you, and thanks for the invitation to give me the opportunity to talk here. So yeah, as I mentioned, my talk will be about Microstretch continuum modeling with a special application to snow compaction. But first, let me give you an overview. I'll briefly introduce solid foams, then talk a bit about the microstretch elasticity, and then our application to the modeling of confined snow compaction with a final conclusion. So first, in general, if you don't know what a solid foam is, the question is what it is. So it's usually a network of here struts or walls that form a network. They have usually a low high porosity, with a low density. There are other interesting properties with it, but the most important are that they usually have size effects due to the intrinsic length scale of the cells. For example, here the bond length, and often under compression they show an inelastic softening behavior. The solid foam we are interested in is, as I mentioned, snow. We can consider snow as a solid foam of ice, as Kirchner stated. So here on the right side we see a CT scan of a snow microstructure, and we can see this looks more or less like a foam. So, but let me first go to the theory. So you all probably know the Micromorphic theory, where the idea is to enrich the standard continuum theory by additional degrees of freedom. So here we have the Micromorphic theory, which adds a tensor quantity, a micro deformation, which can represent the change of the underlying microstructure. This general micro deformation quantity could be like a tensor second order, and has 9 additional degrees of freedom, which is quite a lot. This increases not only the implementation complexity and the numerical costs for solving, but also, of course, a lot of additional constitutive parameters that we have to solve. So we made 2 simplifying assumptions that makes the life easier for us. First of all, we assume that our deformation of the microstructure of the snow can be reasonably well described by micro-rotations and a scalar micro-volume change only. And then in addition we assumed small deformations only, so we can linearize the deformation gradient and of course also the micro deformation. So that's of course nothing new. Kirchner and Steinmann already investigated microstretch theory, but it actually goes back to Ehring. So we have basically the regular displacement degrees of freedom, 3 displacement degrees of freedom, then 1 micro volume change degree of freedom, and the micro rotation, so 4 additional degrees of freedom. But we don't have any higher tensoric quantities, but still able to capture size effects in rotational, shear settings, and also compressive settings, which is important for us. So for strain measures, there are of course different possibilities. So what we choose here is that we kept the symmetric small strain, then we considered a relative rotation between the macro and the micro volume. We have a relative volume change between the macro and the micro volume, and in addition the gradient of the micro rotation and the gradient of the microstretch. Working this out in a, for example, virtual power approach, one can get the work conjugated variables, which are shown here. They are linked by isotropic constitutive variables, where we recover the isotropic elastic stiffness tensor, so it's similar to the classic standard approach. Then we have here additional relative rotational stiffness and a relative volumetric stiffness, which links the stress like with the strain-like quantities. For the balance equations, we consider that we only look at static loading, we neglect any dynamic cases, and also neglect all body forces. This gives us here this balance equation, basically extended balance equation of linear momentum, extended balance equation of angular momentum, and balance equation of volumetric change with the corresponding von Neumann boundary conditions. So we solved this system of partial differential equations in a finite element framework. And therefore we need a weak form, or bilinear form, which looks as follows. So we have the contributions from the balance of linear momentum. So we can see here the classical from the Cauchy stress. Then we have here the terms from the relative rotations, and here the terms from the relative volume change. Oh yeah, I should mention that V, W, and Z are the corresponding test functions for the displacement, the rotation, and the volume change. Then from the balance of angular momentum, we get similar the contributions from this higher order rotation and the contributions from the rotational stress. And in the same way, we can obtain the terms from the balance of volumetric change. And of course, we have a right-hand side. If we discretize this system with same base function or shape functions for the unknowns as for the test fields, and take our isotropic constitutive laws, we get a symmetric matrix for the finite element stiffness matrix, which is nice, so we can use symmetric solver like CG. One interesting feature of this formulation is that we get some kind of unexpected dilatations perpendicular to loading if we are not in hydrostatic loading. So we see here the setup. We have a boundary condition where the displacement in y direction is fixed and the volumetric change. And on the top we consider only a deformation in y direction. And in addition, the point in the middle here is pinned to prevent rigid body motion. So we see here on the right how the micro volume change look, and we see here on the bottom for the uniaxial tensor test with Poisson ratio of 0 that we get additional displacement in x direction and also in z direction, which we would not expect usually. And these induce additional rotations, small but not neglectable rotations. So we think that it's due to the fact that the microdilatation is just isotropic in all spatial directions, but when we just do a uniaxial loading, it's not isotropic. So to minimize the strain energies, this introduces macroscopic displacement into the perpendicular directions.
So this is a micromorphic
this is the microstretch theory. So this is exactly what I showed here. So this equation is here. Oh, I didn't impose any from Neumann boundary conditions. Because it's his name, I think. I think his full name was von Neumann, but I might be wrong. The von Neumann boundary conditions are considered as 0 or 3. Yeah, 0. So no von Neumann. To identify the parameters, we can look at the size effect. So the parameters are directly related to the size effect. So here we have a system which is very similar to the one before. It's a system under uniaxial compression, and we see here for different micro-rotational stiffnesses the response of the system over the system size. So the system size is normalized with the internal length, and here the response is normalized with the classical standard response. And we see that for smaller systems are stiffer, and of course, as I said, increasing CK increases the size effects. So to identify the parameters, we have to do a couple of multiple measurements, or what would also be an idea, what can try is to compare a system to a fully resolved finite element simulation. And this is what is done here. So as an example system, I considered a compression of honeycombs. So here on the right side, we see different systems of honeycombs, all loaded with the same engineering strain. And here is the response of the system. So the blue line here looks a bit distorted due to the projection here. Shows the honeycomb simulation. We can clearly see the size effect again. And now we have all the ingredients to get actually our internal lengths and also our micro-rotation. We have here the system sizes of the Microstretch simulations, the dotted lines, and the honeycomb simulations. This is given so we can fit the honeycomb simulation or the fully resolved microstructure to the Microstretch. In this case it's easy because here we have just discrete possibilities, so we can just take a different normalization. So this is now normalized with H1. If we normalize with the H2, so a bigger size, we see that these parameters here match quite well. So from this here we can now conclude, okay, we know the ratio between the bulk modulus and the micro-rotation stiffness is about 1, and we also know, okay, the smallest system size with which our microstretch continuum can reasonably well represent is about this size. So that's the part to the microstretch elasticity. Now we'd like to go a bit to something else, the application of the model to confined snow compaction. So it's motivated by the question why we can usually walk on snow by just densifying a bit, but sometimes we break through, so it's not quite clear where this comes from. So it could be from a surface crust, but one can also observe this in completely homogeneous snow samples, so that's the question. The experimental setup is therefore compaction of artificial snow, which is in like a glass container here, which has imposed displacement by an anvil, and then we recorded the forces and also took picture of the compression and performed a digital image correlation. So actually the experiments were done by one of my colleagues, Tom Berklow, and yeah, he did most of the experimental work. So here we see now the results. So we can observe a few interesting things. So on the left side we see the recording of the actual experiment. Here in the middle we see the data from a digital image correlation data. And here on the right side we see the force over time plot. And in addition averaged strain rate averaged over the width over the time too. So we can see three things. First of all, we see this like compaction front, which travels perpendicular to the compression axis, so we have no shear bands. Then we see that the bands actually sometimes also travel upwards, so we can see once we shear the bottom, the band travels upwards, and then it reflects again, and so on. This is what we can see here. It travels first downwards, then upwards, and then it bounces forth and back. And we can also see that this bouncing is somehow related to force oscillations in the measurement. So here are more results from different experiments. So we just saw this one here. This one is slower loaded. We see that there's no like interruption in the bottom. And here's another one which is quite interesting, is that the band stops in the middle more or less and then nucleates again from the bottom till it reaches again this point, and then it continues with its pattern. We can also see that we have almost, or we can't really see elastic deformation, so they are very small compared to the plastic deformations. And we were also able to measure the lateral stresses or forces, which were very small. This will become later handy when we like simplify the system. So to use the microstretch formulation in this elastoplastic problem, we made a few assumptions. So the first one is that we splitted the small strain into a total, into an elastic and into a plastic part. Then we neglect rotations for the moment. And we also say that the relative volumetric strain depends on the total relative deformation, which makes sense. So you can have a plastic deformation, and the energy just depends on the difference. But we say, okay, the plastic deformation is way bigger than the elastic deformation, so we approximate this by this term here. So now the volumetric plastic strain contributes to the free energy, and we let it enter as an independent variable to the free energy. And with a quadratic ansatz for the free energy, shown here, we get work conjugated variables. So we get the Cauchy stress and some kind of relative pressure and some kind of higher order, like hyper pressure. With the corresponding boundary conditions, now the balance equations are now a bit simpler. We have the regular divergence of the Cauchy stress equals 0, and this balance here for the pressures. So the inelastic behavior, as we saw, is pressure dependent, and it's also not volume conserving, clearly. So we adopted the Spande-Fleck criterion. That's quite similar to it. It has an additional term here from the micropressure, and from there we can also derive a plastic strain evolution, shown here. So for the yield surface evolution, this is the really interesting thing here. We consider two things. So we observe that the flow stress is influenced by, first, the densification of the material, but also the microstructure. So for the densification, one can obviously see that when we compact the material, it's getting stronger. And this is also what one can phenomenologically observe. There's a power law dependence which was carried out in experiments, and we can, like using the continuity equation for the stress free density here, to get dependence of the yield stress of with the compaction, or the densification. The second part is that we know the microstructure has some kind of residual strength which remains even when the bonds, like from the grains, have broken. So this is more or less related to the friction of the bonds, and in addition the structural strength from the bonds. There are two competing mechanisms. So we have one, on the one hand, of course, the softening from bond breaking, but there's also a competing mechanism by the H-hardening from the rapid sintering. So we have to consider that snow is actually a high temperature material, so it's close to its melting point, so the sintering processes are quite fast, so the range of seconds. We can write these two competing mechanisms into this strain rate dependent evolution equation. Well, so we have all the ingredients now for the plastic deformation. So for the governing equations, we abuse the observation that we have very, very small lateral expansions, so we can approximate the Poisson ratio with 0 and the alpha from the Spande-Fleck criterion with 0.5, and this leads then basically to a one-dimensional problem. The one-dimensional stress, the plastic strain is one-dimensional. The yield function looks then as this, when we take the balance equation of volumetric change into account, and the yield evolution is also simpler now, so everything is one-dimensional. We can link this theory here to the classical Eifantes strain gradient theory, when we now consider this volumetric change as a penalty parameter, so we make it very large. Then the difference between the micro volumetric change and the macro volumetric change gets penalized, so it's getting closer and closer together. So in the limit case, the micro volumetric change equals the macro volumetric change. Then when we take, for example, for beta, this relationship, so the ratio between the initial and initial macro and the initial micro modulus into account, we get to these equations. So this is basically a strain gradient theory. And this equation we then solved in a self-consistent scheme with the boundary conditions. As mentioned, on the bottom we have 0 or no displacement. On the top we have the displacements imposed by the displacement rates in the same way as we observed displaced experiment. And of course, the initial conditions are a stress-free and a strain-free state, and we consider a fully aged material, so the more or less perfect material. To account for material inhomogeneities, what we definitely have in snow, we made a Weibull distribution of the initial strength, sigma, with the Weibull parameter of beta equals 5. So these are the parameters, the remaining parameters for the system. And then by carrying it out and do the simulation, we get following results. So we see here again the experimental data, it's already shown, and here on the bottom we see the simulation results. So we can see that the simulation, quite nice, reproduces this pattern of the compaction band which travels through the material and then reflects. But we can also, depending on the Weibull distribution, or actually depending on the material inhomogeneities, get these like bouncing or these jumping patterns. When we have here, for example, a strong strength, then the compaction band might jump and then nucleate from the bottom again. We also see that the force time plots actually fit quite decent.
And how can you catch this jump from the simulation?
Pardon?
From the simulation, how
yes.
can you catch this jump?
So the jump is just to the from the distribution of the strength. So we don't have a uniform distribution. So as I said, a Weibull distribution of the strength. So when here in this case, it's just like a statistical property. So here is a high strength now. This now the band starts from the bottom.
So
I forgot. Oh, sorry.
So the sum from the beginning.
Pardon?
It is a sum from the beginning distribution of strength.
Yeah. It's the initial. It's that's the initial distribution. Yeah. What we can also see is for fast deformations, so here on the left side, we see that we have, so what we see here is the position and the local compressive strain, and each line here represents one time step. And we see that for fast deformation, so when we have a big number for the recovering, for tau, then we get this one band. So we see that the one band travels through the material, and then after that a homogeneous compaction. In the transition phase, where both mechanisms, the sintering and the H hardening, are almost the same like rates, we see this here a second band, and then homogeneous deformation. For slower deformations, we can like see crazy patterns like multiple bands or bouncing bands. So to conclude, we have this the strain localization and the deformation band propagation are a generic feature of this deformation processes if the shear softening outweighs the densification induced strengthening. So the pattern is just due to the modeling of the yield surface evolution. And then we also get these interesting deformation oscillations with the bouncing bands and the intermittent bands. And we can also reproduce quantitatively the force time curves. So the breaking through the snow, coming back to the beginning, as I said, can also appear in homogeneous snow, and it might be an indicator of the tendency to strain soften. So it doesn't probably help when you're out in the snow, but it's quite an interesting phenomenon. So next steps are, of course, to use a fully coupled and also three-dimensional theory for investigating the problem. And with this, I would like to close my talk and thank you for the attention.
One of your introductory slides was shown that it was isotropy of snow.
Pardon?
It's constituted behavior isotropic.
Yeah.
If I remember correctly, there are
I think the elastic properties are relatively isotropic.
Yeah.
It depends, of course, because like snow is not snow. There's like billions of different snows, and depends when it's like overnight and when you have like when it's melted and then frozen again. Then of course it's getting anisotropic. But our like lab snow, which was made artificial, it was pretty isotropic.
Very fresh, yeah.
Yeah.
Isn't it strange to see the word plasticity as you shift to the shape?
Yeah, that's true. It's not a real plasticity. It's like the modeling is kind of like in a Yeah, it was like carried out in a plasticity framework. So maybe it's not real plasticity anymore.
For three-dimensional simulation, show your boundary conditions for lambda,
Yeah.
which is set to 0.
Yeah.
What was the motivation?
Oh, this was just like academic example to see what happens under different conditions. So there's no real reason for it. But when you're not set at 0, then in the uniaxial tension, there's nothing interesting to observe with the because then it's just completely homogeneous. The microstretch.
The choice of your, let's say, micromorphic variables was only really purely the computational reason with less degree of freedom, so it's also a microscopic motivation.
It was mainly for easier implementation, so there's no. I think one can even better argue with a like micro shear somehow, so that you don't take like rotations into account, and instead like more like a micro strain, for example, might be even a better approach. But yeah, this was our first attempt.